Hey everybody, welcome to the Chapter 4 guided assignment. We've actually got 6 problems we're going to try to walk through together to kind of, I guess they're representative of the types of problems you'll see in the homework and then on the exam, of course, for this chapter. So the first one is a combinations problem. So as we talk about combinations and permutations, we have to be able to recognize the difference between the two. We're lucky when a problem tells us combinations or permutations, but sometimes they don't, and they try to give us a context clue. So a combination is different ways that we can select a certain number of items from a larger group of items. So in this case, it's how many ways can 3 items be selected from 6 items. So if I had, let's just say they're balls with A, B, C, D, and F on them. I could take ball A, ball B, and ball C. That'd be one way to take them. I could take ball A, ball B, and ball D, ball A, ball B, ball E, ball, etc. Okay. So with combinations, the order is unimportant. Meaning if I grabbed A, B, and C, I would consider that the same as if I grabbed C, B, and A. So the order that you take them in doesn't matter. With permutations, on the other hand, the order does matter. So we would, like say something like, I'm trying to think of an example where the order that people finish in matters. So let's just say like a race, okay? We want to know if we have 10 runners and we want to know how many different ways can those 10 runners come in first, second, and third. It wouldn't be the same thing if runner A came in first and B came in second and C came in third, or if runner C came in first and B in second and A in third. Those would be 2 different things. So with permutations, the order matters. And with combinations, the order doesn't, okay? So here we are given, we have 6 items to be, and we want to select 3 items from the 6. How many different combinations are there? So in your book on page 175, there's the formula, which is n factorial, so big N factorial, okay, which factorial means where you multiply if the number is 6, that would be our big N, the number of items. It would be 6 times 5 times 4 times 3 times 2 times 1. Divided by little n factorial, which is the number of items you can select, which is 3 times 2 times 1, times big N minus little n factorial, so 6 minus 3 factorial. So we could solve this by taking 6 factorial. So we could just say, so again, let me just show you the notation. So number of items will be notated as big N, and items taken notated as little n. So we could say that the combinations is big N factorial. So in Excel, you would write this as fact for factorial, and then big N. You know what I'm going to do? I'm going to put those numbers in for us here. So in this case, the number of items is 6, and the number of items taken is 3. So the number of combinations will be fact. So the factorial of big N, which is 6, divided by little n factorial, times big N minus little n. Whoops, I didn't put, we have to do the factorial of big N minus little n. And then we close that and close that. So that would be the formula if we wanted to make our own calculator. And it would come out to 20 different combinations. Luckily for us, Excel has a function for this called COMBIN for combinations. And there you just choose the number, which is the big N, 6, comma, the items taken, which is the little n, 3. So that's usually a way easier option for most of us. But I just wanted to show you how the formula works in Excel. You can create your own calculators, but here we have a function called COMBIN for combinations. So I'm going to say there's 20 different ways that I can take 3 items, 3 items from a group of 6 as a combination. In other words, where the order doesn't matter. Okay, and then it tells us to use the letters A, B, C, D, and F to identify the items and the list of the different combinations. So in essence, we could take ABC, ABD, ABE, ABF, ACD, ACE, ACF, etc. So this is going to be our correct one. We'll check our work and make sure we're good, and we are. So that's combinations. The second problem is going to do permutations. Okay, so again, there's a whole formula for permutations in the textbook, which is just the factorial of big N divided by the factorial of big N minus little n. So it's actually a little bit easier. So I'll show you. We can do, so this is how many permutations of 3 items can be selected from a group of 6. So we'll do permutations. We have the same numbers here, 6 and 3. So if we were going to make our own, we would say this equals, the numerator equals the factorial of big N divided by factorial of big N minus little n. And we'll see that there's 120 different permutations. So it makes sense that the permutations are going to be higher than the combinations given the same number of items and the same number of items taken. And the reason it makes sense is because now, instead of A, B, C, and CBA being the same thing, we're going to count ABC as one, BAC as another, BCA as another, CBA as another. So we're always going to have more permutations than we have combinations. Again, we can use the Excel function, which is permut, P-E-R-M-U-T, and then it's the number 6 and the number chosen 3. And you'll see it gives us the same answer as my calculator. So we'll say 120 possible permutations. And then it will ask us to use the letters A, B, C, D, E, and F to identify the items. And we can't really do, I mean, we could, I guess, but we don't want to list all 120. So it asks us just to list the permutations of B, D, and F. So we would say, well, we could have B, D, and F. We could have B, F, and D. We could have D, B, and F. We could have D, F, and B. And we could have F, B, and D, and F, D, and B. So we get all those permutations just of B, D, and F. We'll check our work, and we'll move on to number 3. All right, so here we have a deck of playing cards. And so we have to figure out some basic probabilities here. We know that there's 52 cards in a deck. If you didn't know that, you do now, okay? So we would say that of our probabilities, the probability of grabbing any one card is 1 out of 52, okay? So then we have to ask ourselves, if we want to figure out other sorts of probabilities, we'd have to ask ourselves what are our sample points. So the first one is, what is our sample points in the event an ace is selected? So we would say, well, there's 4 aces in a deck of cards, so there would be 4 sample points, okay? The second one is, how many sample points are there in the event clubs are selected? So we have all the way from a 2 of clubs, so 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace. 13 total clubs. So there's 13 sample points in clubs. And then how many sample points are there in the event a face card is taken? So a jack, a queen, or a king. So there's a jack, a queen, or a king for each suit. There's 4 suits. So 3 cards times 4 suits would be 12. So now they want us to find the probability associated with each of these events. So let's see, so I did ace, I'll do club, and we said there were 13 of those, and face card, and we said there are 12 of those. Total cards in a deck is 52. Okay, so our probability of an ace is just going to be the number of aces in the number of sample points divided by the total number of cards in the deck. So it's 4 out of 52, or 0.07692. It wants us to do it to 2 decimals, so that's going to be 0.08. So if I randomly pick a card, I've got an 8% chance of it being an ace. So the probability that it's a club is going to be 13, because there's 13 clubs out of 52. Now, we could probably have guessed this one. We know there's 4 suits in a deck. So we would guess it would be 1/4, right? And it is 0.25. So the probability of me selecting, if I select a card from a deck, the probability of it being a club is 25%, or 0.25. And finally, the probability that it's a face card is going to equal 12 divided by 52, or 0.23077. So 2 decimals, 0.23. Check our work. And luckily we got them all right. Not luckily, we're smart, right? We can figure these things out. All right, let's go on to number 4. All right, so number 4 tells us a CBS New York Times poll of 1,000 adults in the United States asked the question, do you think global warming will have an impact on you during your lifetime? Consider these responses by the age groups below. So we have people 18 to 29 and people 30 plus. That was the 2 age groups. And then we have yes, no, and unsure in each age group. So the first one says, what's the probability that a respondent 18 to 29 years of age thinks that global warming will not have an impact during his or her life? So in this case, you could be tempted to take 131 divided by the total, which is 1,000, and come up with 0.131 or 13.1%. But we're limiting our pool here to only respondents that are 18 to 29 years of age. So I'm going to go ahead and just kind of recreate this data here. So I have yes, no, and unsure. And then I have my age, 18 to 29, and 30 plus. And then our responses were 134 yes, 293 no, 131 yes, 432 no, 2 unsure, and 8 unsure. Okay, and if we want, we could take totals. Starts to look like a pivot table, doesn't it? And then we can take totals this way. And we can see it comes out to 1,000 total responses. Okay, so the probability that a respondent 18 to 29 years old thinks global warming will not have an impact. So we're going to first limit our data set in this case to people that are 18 to 29 years old. Okay, so the probability that given that we're limiting our set to 18 to 29 year olds, that they are a no. So the probability that our response is no, given, which is kind of a term here, that they're 18 to 29 years old. That means we're going to say the probability is 131 people out of 267 total. So these type of questions sort of limit our data set. We're not looking at the whole data set of 1,000. Instead, we're looking at this smaller data set of just 18 to 29 year olds. So we get an answer of 0.4906. You can see that these different problems have had different numbers of decimals they want me to round to. So it's important that you pay attention as you do this. So the second question is, what's the probability that a respondent 30 plus years of age thinks that global warming will not have an impact? So here, we're not going to limit to this data set. We're going to limit to the 30 plus data set. So now we'd be saying, what's the probability of a no answer given someone is 30 plus? So we would say that probability is 432 out of 733, because there were 733 total respondents over the age of 30, and 432 of them said no. We come up with a 0.5894. Remember, if you don't like doing the rounding in your head, you can always do this and then reduce the number of decimals. Whoops, I did it wrong. And it will do the rounding for you, which is kind of nice. All right, so now the question is, for a randomly selected respondent, what is the probability that respondent answered yes? So now we're not limiting our data set to 18 to 29-year-olds or 30 plus year olds. We're just saying, what's the probability that they said yes? So we would have all yeses, 427, out of the total of 1,000. So the probability of yes, no limitations, is 427 divided by 1,000, which should be 0.427, right? All right, so now it wants us to do some interpretation. It says, based on the survey results, does there appear to be a difference between the ages of 18 to 29 and 30 plus regarding concern over global warming? And when we look at this data, we would say, well, more of the 30 plus year olds think it's not going to impact them than the younger generation, right? So we would say it appears older respondents are less concerned about global warming being a threat in their lifetime than our younger respondents. We'll check our work. And we got it right. All right, so we'll move on to number 5. A survey of magazine subscribers showed that 45.8% rented a car during the past 12 months for business reasons. 54% rented a car during the past 12 months for personal reasons. And 30% rented a car during the past 12 months for both business and personal reasons. Okay, so what that means is that there's some overlap between these two groups, right? That 45.8% of people just for, let's see, just for business, and 54% just for personal, or not just, but for personal or for business, and then 30% for both. Okay, if we were to draw a Venn diagram, we would have like these overlapping circles, right? With 45.8% in one circle, and then 54% in the other circle, and where they overlapped, we would see that it was, what was it? 30%. So I'm actually going to show you a little picture from the book to give you an idea of what I'm talking about. So here, in this situation, we could have event A, that they rented for business, event B, that they rented for personal, and then this middle space would be the space where they rented for both business and personal. So we could take the intersection of event A and B, which would be all of these spaces, or we could look at the intersection. Oh, sorry, this is the union. I said it wrong. So this is the union of A and B, which is the probability of A plus the probability of B, and then minus the probability of the union. Okay. The reason we want to subtract this is because if we take the probability of A and the probability of B and the probability of this middle spot, we'd be counting this too much. Even if we just took the probability of A plus the probability of B, we'd be double counting this union where they overlap each other. So to find the probability of the union of A and B, we're going to take A plus B minus the union. Okay. All right. So let me show you what that looks like now with our homework. All right. So what is the probability a subscriber rented a car during the last 12 months for business or personal reasons? So we would say, okay, so the probability, I'm going to say probability of business, running it for business, is 0.458. And the probability of personal is 0.54. That should be a big P right there. And then we would say the probability of the union, in other words, I don't know if I have a key on my keyboard that will work for this, probability of the union of B. And if you'll notice in the textbook, it looks like a big U, which I don't have. So I'm just going to put U, B is 0.3. So the probability then of B or P will equal the probability of B plus the probability of P minus the probability of where they overlap each other. So we'll say 0.698. So the second question is, well, what's the probability that someone did not rent a car in the past 12 months? And so then we would have to agree that the probability that they did rent a car plus the probability that they didn't rent a car would equal 1. And I think that we can agree to that. We can say either they did rent a car or they didn't. So this is telling us that people rented a car for 0.69 or 0.698, or 69.8% of people rented cars, okay, either for business or pleasure. So the probability that they did not rent is just going to be 1 minus the probability that they did rent. Right? Because in the end, these have to add up to 1, that they didn't rent or that they did rent. I mean, that they didn't rent or that they did rent. So we're going to put 0.302. We're going to check our work. And we're all good. Okay, the moment you've been waiting for, the last problem. All right, so this is just using, instead of doing it as a word problem, it's using similar, or it's using the proper, I guess, mathematical notation for the same concepts we've been learning. So we have two events, A. We have the probability of A being 0.5, the probability of B being 0.6, and then the probability of the intersection, so that's part in the middle, being 0.4. Okay. So then it wants us to find the probability of A given B. And so this little line means given, which means we limit our data set to just B. So mathematically then, we just need to know the formulas for this. Although I'll tell you, it is actually way easier when you can see it like as a pivot table. So that's kind of interesting. Anyway, so I'm going to pull up the formula here in the book so I can show it to you guys. That might make life a little bit easier. So the probability of A given B unfortunately, they use M in the book here. Okay, so this is the probability of A given M is just the probability of the intersection of A and M divided by the probability of M. Okay, so pretend that M is a B. So we'd say, so I'm just going to come down here and I'm going to say, okay, what's my probability of A? That's given to us as 0.5. And our probability of B is given to us as 0.6. And then the probability of the intersection, which I don't have a button for upside down U. So I'm just going to do of A intersection B. Okay, that's what we'll call it. And that's 0.4. So if we look at our formula we just did, the probability of A given B, probability of A given B is just going to equal the probability of the intersection of A and B divided by the probability of B. So we have 0.6667. All right, and then the probability of B given A, oh look, here it is, I found it with A's and B's instead of A's and M's. So the probability of A given B is the probability of the intersection of A and B divided by the probability of B. And then the probability of B given A is the probability of the intersection of A and B divided by the probability of A. Okay, so the probability of B given A, whoops, my capitals, that's a big B, just see a big B there, okay, is going to equal the probability of the intersection divided by the probability of A. And that's going to be 0.8. And then there's a rule that we have to know if we want to tell if A and B are independent from each other, okay? Meaning, remember what we're talking about are two events. So if two events are independent from each other, then the probability of A given B, so let's just say, so these two are independent because the probability of A given B is not equal to the probability of A. So we would say something is dependent on the other one if the probability of A given B is equal to the probability of A, right? Then they would be dependent on each other. So we'll check our work. Oh, except that I just messed this up. Sorry, we'll say they're not. Let's say, are they independent? No, they're not independent. So, and they're not independent because the probability of A given B is not equal to the probability of A. In other words, if the probability of A given B is equal to the probability of A, we would say those two things are independent. I'm sorry if I confused you with my little screw up. In this case, probability of A given B is not equal to the probability of A, and so we would say it is not independent, meaning it is dependent, that A and B are related to each other in a dependent way. All right, well, I hope that was helpful as you go into the homework. I can submit it, get my easy A for following along, and I hope, like I said, that was helpful, and I hope you have a great rest of the week.